everybody wants a chance to talk to one another. We'll give you more time afterwards, but we have a really special guest. This is another Chancellor's Professor at UC Berkeley. He's a Chancellor's Professor in Computer Science, Joe Hellerstein, who is also the founder, or co-founder, I should say, of a company called Trifacta, which he will be sharing more about. But I want to just tell you a bit more about him. He has been doing research on data-centric systems and the way they drive computing. He's the Chief Strategy Officer of Trifacta, and he has won many awards from the Sloan Research Fellowship and MIT Technology Review TR10 and TR100 lists, Fortune Magazine's Smartest in Tech list, and 3 ACM Sigma Test of Time awards. So he is tried and true, and it's a real pleasure to welcome Joe.
Thanks for having me. It's good to be back home at Berkeley. This is great. I've been running around like a chicken with my head cut off, giving talks around the country. So this is a homecoming, and it's really nice to be back. Today's talk is I have slides. I have a demo because I want to actually show you. It's a talk about interaction, and if you don't see how you interact with the damn thing, you don't really know what it's about. I will spend some time talking and then hopefully keep it relatively informal. The last time I gave this talk earlier this week, we had a room of about 20 people, and it was a little easier. But we'll try to open it up for questions and try to make it interactive. So Trifacta, and I'll talk about this. It's a company that came out of research that was done here at Berkeley in collaboration with colleagues at Stanford. And sort of the way to think about the problem space that we're solving is relative to where data was 10 years ago, there's much more complexity in the kinds of data people are gathering. We used to just have business system data about bills and employees and things like that. But now we're getting data generated by machines, the Internet of Things. We're getting data generated by software at great scale. Pretty much any piece of software these days of note is generating log files faster than you can imagine, and formats keep changing. So there's a lot of complexity that people who are dealing with data are facing these days. Interestingly, at the same time, the products we're building out of data are becoming simpler and more consumer-oriented. So we're building things like recommender systems at Amazon, for example, or at Netflix, something anybody can understand. We're building fraud detection algorithms, right, at credit card companies. Again, things that say yes or no. A very simple data product at some level, very consumable. And data visualization is part of common culture now. The New York Times hired my colleague's student, my co-founder's student, to be he's a reporter with a byline, Mike Bostock. But what he really is a software engineer. He built D3.js with Jeff Hare. And his job is to produce interactive visualizations for the New York Times. So we're building things that are really commercial products. And so simplicity on the right, complexity on the left, how does that work? Well, with a lot of sweat. It's pretty much the story. So there's a lot of pressure being put on the people in the middle. And I think folks who are at this workshop know that this is a wonderful opportunity if you have the expertise. But you've got people there. They're relatively rare. They're hard to hire. And they're spending a lot of time doing these tasks, whether they're sort of data scientists in a technical manner or they're business data analysts. Right? And there's really a choke point from an ecosystem perspective in not having enough of those people and not having them be efficient enough. And when you sort of break things down, and we did break this down both in formal user studies in academia and now as we've been taking products into market, talking to people in the industry as well, we imagine, right, that the time of data analysis sort of split between the work that happens in these big data engines like Hadoop and MapReduce and SQL, and then the work that happens in analytic tools, whether they be visual data analytic tools like business intelligence tools, or predictive analytics tools like SAS and R and MATLAB. This is kind of what we think about when we think about data analysis. But when you go talk to business analysts or data scientists, they will tell you over and over that 80% of the work in any data project is in preparing the data for analysis. And this has become such a common thing to say that there's a guy on Twitter whose handle is Data Borat, and he posted famously about 9 months ago, 80% of work in data project is preparing data, 20% is complaining about preparing data. Right? So, but it really does come up in real life over and over. So this is the bottleneck. It's a human bottleneck, and it's a sort of busy work bottleneck. And it's just a damn shame, right? And so Trifacta, in essence, is trying to attack this problem in the middle, provide the the tools for data analysts to work with in their everyday tasks to make them far more productive and far more efficient, and to leave the innovations that are happening here and here in place and let them continue, and to fit into that context and reduce these bottlenecks at the human level. And we hear this from all kinds of people. Data analysts, sort of business data analysts, they would like to have self-service access to data. So if you're in the sales department of a modern retailer, you want to be able to get the data about what people are doing in buying patterns and use that yourself to figure out how to sell better. And so folks like that, they don't want to have to go to the IT department and ask for an extract from the business data warehouse to get information. And they certainly don't want to go to the IT department and convince them to host a new data source inside the data warehouse, because that takes months to years to get vetted, right? So these folks want to do self-service data analysis. In the middle, your technical data scientists, these are folks at banks who do fraud detection or people at internet companies. They don't want to be wasting their time writing Python scripts cleaning up their data. They want to be doing modeling and statistics and all the stuff that they were trained to do as experts in data science. And so these folks are really hurting as well. And then the poor folks in IT who are supposed to support all these guys, they actually don't want this job. They don't want to spend their time prepping data either. And in fact, we're in interesting times because if we can make everybody more productive, nobody loses their job. Because there's so much work to be done around data these days that basically everybody just wants to get more efficient. And so everybody would like to see these things become more self-service and easier to use. So about, 13 years ago, I was a professor at UC Berkeley, which I still am. And I had a student that I was working with. We had a project that I started in the mid-90s on interactive processing of very long-running jobs. Over data. And one of the tools we built was a tool called Potter's Wheel, which tried to address this problem of data transformation in a much more visual environment. So prior to this work, most of the efforts that were done on very large data sets were done by writing code. So if you had to clean up data, you would write things in Perl, you would write things in SAS data step or other languages for working with data. It was a very sort of technical task. Or if you had small data, you'd load it into Excel. Right? And so what we tried to do is build a spreadsheet experience over very large data. So you had the illusion that you had tens of thousands of rows when actually you had gigabytes and gigabytes of data in 2001. And then we designed a language that was focused on data transformation, focused on the tasks that people do in prepping data, as opposed to most of the things we do with spreadsheets, like calculations. And then what we said was, let's make sure that we have a language that's well suited to this task so that you can pull down a transform in this language and instantly the screen will update with the outputs of your choice of transformation. So this language is at an appropriately high level. It would give you immediate visual feedback so you could see if you're doing things well or doing things poorly, whether you're making progress. And in the background, it would do discrepancy detection. It would try to find if there are outliers at any given time while you were massaging your data, or if there were things that didn't match the data types and so on. And all this was being done in a language underneath this visual interface. So that would give you a sense of what was the lineage of the data. How did the current state of the screen come about? And if you didn't like it, how could you undo things or redo things easily? That was all done because we had an appropriate domain-specific language for data underneath this. And this was interesting work, and we thought it was super cool. And it had a kind of clunky user interface because we didn't do user interfaces back then very much in computer science. And it kind of sat on the shelf. And so that's OK. And in fact, today, there's a whole bunch of startup companies building the moral equivalent of exactly this now. So I'm happy to say, many years later, there's a bunch of sort of visual interfaces for data transformation. And it's certainly a step forward from writing code. OK. But the real problem with this over time that we realized was that you can change somebody from typing extract string from column in text to extract column string, right? But they're still specifying the same thing, right? But just by making things visual, you don't make them easier. The burden of specification is still on the user. The computer isn't helping at some level. The computer is just doing what you tell it to do, which is what in the 20th century computers were for, right? In the 21st century, though, and maybe I'll skip a slide because I like the next slide better. I think it's more illustrative. We're used to computers doing stuff like this. You start typing, and it already knows what you're going to finish typing. Right? The computer's actually thinking on your behalf. It's doing things that for you are obvious. Now the computer can help with that. So Google has this feature called predictive search. You start typing. It knows what you're going to finish typing in advance, and it shows you a probability distribution, which is just a ranked list of likely outcomes in order of probability of what you'll finish typing. And we kind of understand how this works at a high level. Right? They know you and what you do and what you're interested in. They know all the data on the web. And they kind of use those things to predict what you're going to do now. Right? And so That's all very nice. It's very data-driven. It's got some statistics in it, and it's improving your interaction. And Google claims in their marketing materials for this that it saves every individual on Earth something like 2 seconds a year, which when you add it up is kind of nice, right? Thank you, Google. They just gave us back a whole bunch of time as a race, okay? So that's cool. So can we have something like this in this much more technical domain of manipulating data for analysis? So I am going to go back a slide now and kind of show you, this is the world of Potter's wheel and these traditional tools that people are now off in the market doing. The user lives, whether it's visually or in terms of text, they live in the plane of writing code. And somewhere underneath it is there's a plane of visualization and interaction that they can get to. But the way that this works is they author a transformation script on their data to see if they can get it in the shape they want. And then because their data is big, they take maybe a little bit of it, a sample of some kind, and they push that sample through their script. And then they use this cool computer stuff to get a picture of the data, or maybe to run a statistical analysis of the output to see if it was any good. And this is kind of the way the world has been. You know, the human drives, and then they can get the computer to do stuff for them. And so what we tried to do with Trifacta, to skip ahead, is to, well, sorry. So let me do a brief interlude, because there's really research that drove this, and I wanted to make sure at a place like Berkeley I talk about this. We tried to say, what could computation do a la Google to help with this interaction problem where users have to specify everything? So this was a collaboration between myself and then Jeff Hare, who's an alumnus of Berkeley and went to join the faculty at Stanford, and his student, Sean Kandel. And Jeff and Sean are human-computer interaction experts. So they think about data visualization, and they think about how do people work with computers. I'm kind of a database guy. I'm a systems guy. And so we came together on this problem to say, how can we take the work that I did with my student back in the early 2000s and use things like machine learning to make the interaction better? Okay? And so the way this works is, like Potter's wheel, we still have a nice high-level step-by-step language and feedback as you go. But along the way, sort of like Google's predictive search, we have machine learning predictions on like what transform in our language might you want to perform next based on your interaction with the data. What types of data do you have just based on the strings we see? And give you visualizations of the quality of the data that are meaningful. And in essence, what we're trying to do, sort of like predictive search, is marry your context, the things you start typing, your intelligence, your understanding about the data, with the machine intelligence and what it's able to predict about what you would have done anyway to remove some drudgery from you. Okay, and we wrote a series of papers and user studies and so on. But the way to think about this at a high level is we're flipping this interaction paradigm. We're saying, no, the user's not going to live in the world of code. We're giving the world of code back to computers. The user's going to interact with the visualization of the data. So the system will pull a sample for the user and throw it up in some kind of best effort visualization. And maybe the data is kind of horrible to start with. So maybe it's just like a page of Craigslist listings. And if we tried to plot a chart on it, we get a bunch of bars of length of height 1 because every row just looks different. Okay? But what can the user do? They can say, this 1 is interesting to me, and this 3 is interesting to me. And then the system, with those 2 simple gestures, much like Google, can give a ranked list of predictions on what code you would have written. And what it's saying is, I think the most likely thing you're trying to do based on highlighting 1 and 3 is to extract from this description column after the space and before the BR. And much like Google, we can show you a visualization of that prediction instantaneously and say, if you choose this thing, you'll get a new column that'll look like this, which pulls all of those integers out of those strings and puts them in a column where they're all integers. And here's the distribution of values in that column. And you can look at that and go, yeah, that's exactly what I wanted. I'm sure that's right. That's the distribution of numbers of bedrooms in clearly not San Francisco, but someplace much cheaper than that. Right. OK, so that's the flavor of this. And we call it, much like Google calls it predictive search, we call this predictive interaction. It's predicting the interactions you would have done in the traditional tool and taking the burden of specification from you. OK? So that's the flavor. And the idea is to kind of put this sort of layer of software in between the traditional engine stuff and the sort of traditional data visualization stuff. OK? And so there's a lot of tasks, and I won't get to show you all of these in the time we have today, but there's a lot of tasks you need to do to transform data. If you haven't gotten your hands on this, there's things like when you crack open a data set, what the hell is in there? And is it of any use? And is the quality any good? What do we mean by quality? Well, statistical outliers, type mixtures, just things not all of the same type, they're all mixed up. And then this one actually turns out to be relatively time-consuming in the modern era. The analytics software at the top of the stack, it wants all the data kind of racked up in columns. Because if you're going to run a statistics algorithm, or you're going to draw a chart, you need a big set of numbers, right? And if I give you a horrible log file that's all mixed up, I got to convert that log file to something where all the numbers are neatly racked up and can be analyzed by my software. So I need roughly rectangular data. And what's coming out of log files and all these kind of things these days is not rectangular at all. It's nested, and it's text, and it's horrible. Okay, so this shaping of the data is important. Oftentimes, the data set you have isn't the whole story. You need to enrich it with other data that you know about from your organization. Maybe it's public data. Maybe it's the enterprise data warehouse data that really knows about your customers and has the records. You want to join that with your log files and so on. And then finally, when you're done with this whole thing, the traditional thing was you spend some time in Excel, you manipulate the data, that's great, you get it looking just right, and you send that spreadsheet to somebody. And what do they have now? They have the output. They have data, right, which has been boiled and cleaned and ironed, and they don't know where the data came from or what it was. What we really want to do is we want to be able to reuse not just the data product, but the process that you spent the time doing to get there. Right? So you want to understand what were the sources, what were the sinks, and what was the work that you did along the way. And then be able to reuse that in whole or in part in other applications or other tasks. So these are all pieces of this kind of data transformation life cycle. I won't brag to you about what our customers say, but 2 weeks turns into 2 seconds. 6 weeks turns into a day. There's people who didn't used to be able to use this technical stuff, and now they can. That kind of stuff. So we have a bunch of customers from the very large to the more small, and they're doing all kinds of things. And sure, it's good for your business, so you should spend money on it. And I'll skip that slide because that's not this audience. Okay. I think this is the part that's sort of more fun. So I parked at 5 minutes to the hour and booted up my VM, and hopefully this will all work. So what we're going to do is we're going to transform some data and clean it up so you get a sense of what this interaction model and why this is really something quite new. And the task we're going to do, imagine, if you will, that you work for a telecommunications company, that one of our customers is Orange, which is a telco in France, one of the big cell providers in France. A standard analysis task at a telco is what's called churn analysis. You want to figure out if your customers are leaving the service, and if so, why. And if they're going to leave the service, you'd like to predict their leaving before they leave so that you can do something about it, like give them a coupon or what have you. Right? It's called churn analysis. Happens all the time. And the way we're going to do this is we're going to start with customer data, which comes from our data warehouse, and it's nice and neat, nice and neat. All right? And then we're going to have call detail records from our cell towers, which are just log files for every call that ever happens, and they are not neat at all. And what we're going to do is we're going to boil down those call detail records into per customer statistics so we can see for every customer what's been their experience on average with the system and see if there's a correlation between customers' perception of quality, things like how often do calls get dropped, and their likelihood of leaving. Okay? And hopefully I'll get all that data racked up and put together in the next 5 minutes. So let's see if we can do it. So the first thing we're going to do is we're going to load in this nice clean data from the data warehouse. So we'll call this the subscribers table. And this is a nice, we'll look at a JSON file, which is a sort of typical format you get these days for interchange, right? It's generated by software logs and also used for interchange. So we'll load the subscribers.json file into the Trifacta interface. And we'll look at it, and here it is. And sure enough, this is pretty nice, clean data. This, since you do work at a telecommunications company in this scenario, you see your international mobile subscriber ID, which everybody knows about that. That's the customer ID for cell phones, okay? And you have their contract extent and how long they were a subscriber and status, and you got some nice visualizations. And all that was nice and neat. But let it be known that when the data came into Trifacta, it looked like this. All right? Actually, it was worse than that because this is broken down by new line, and if I try to undo the new lines, Trifacta will say, really? You really want to put that all in one cell? So one thing that we're doing right away is there's some dead obvious things about cleaning up data and just getting your first eyeballs on it, where we can often infer exactly what you're going to do with no interaction. Right? And we might want to interact with this more. Like, for example, this contract thing is nested. It's got a start and an end nested into a single column, and this sort of nesting happens in JSON all the time. Okay? And something we might want to do is say, I'd really like to pull out the start dates from this thing. And so here, let me go show you a little flavor of predictive interaction. One thing we could do is we could hover over these histograms. It says there's 1,425 instances of start, 1,425 of end. I could click on the start bar, and I get a recommendation, much like in Google, all right, to unnest that column into its own column. Unnest that key from this nested thing into its own column. I could accept that and add it to my script, but just for fun, let me show you another way to do that, which is I could just highlight an example of this. I'm looking for the start stuff. And again, we get a list of recommendations, the first of which does the same thing. Okay, so by interacting either with visualizations or with the data, the text of the data itself, we get recommendations from the system about tasks we might want to do with the data. And sure, let's go and unnest this thing. And you can see that everything we're going to do is going to turn into code in a high-level language up here. All right? So we're actually predicting statements in our high-level language, which, by the way, is called Wrangling. It was designed for the task of data wrangling. All right, so let's assume that the subscriber's data is good enough. It's the way we want it. Let's go look at that call detail record data. So let's pull that in. And this is going to be the hard stuff. That was easy. In fact, that was almost completely automatable. And I want to impress upon you guys the fact that data wrangling is not automatable in general. Because there's such a diversity of inputs and a diversity of things you might want to do with the data, there's no algorithm that knows what you want to do with all the data in the world, right? So this ends up requiring human interaction. So let's pull in these call detail records. And this is what Trifacta manages to do without any help, all right? And again, if we undid this, the rows that come out of these logs kind of look like that. And Trifacta said, hey, I think you could split it by tabs into columns. And that's OK, but we're going to need to do more work. Okay? And lo and behold, here's an IMSI, which is our customer ID. We know that because we're telco folks. And so we can tell Trifacta, oh, we like that. That's good. IMSIs. Let's highlight that. And it's going to recommend something to us. It's going to say, hey, I think you're trying to pull out 4-letter capitalized terminology out of this thing after delimiters. And that's not quite right. And we could fish around in these recommendations and look for a better one, or we could just give it another example. And it will learn from these examples, okay? And it will re-rank its recommendations based on your multiple interactions. So now we highlighted 2 things, and the top ranked thing is extract after column 2, after a delimiter, and before a delimiter. Okay? Is that right? Well, maybe. How would we know if it's right? Let's look at the output. The output ranges from the value 208 and something to 208 and something. So there's actually no surprises down there. These all look about the same. It's of type integer. That's a good sign. All right, there is a whole bunch of valid versions of integers, and there's one row that's not an integer, and guess what? It's the first row. It's the header, right? So that's all good. So this looks pretty good. So we pulled out our IMSIs. I need to tear this thing apart. I want my date times and my durations. And you can see you want to do it visually, right? You want to actually just point at the data. So let's do that on the screen. Highlight a slash here. And it'll say, oh, are you trying to split this up by slashes? I can do that for you. Okay. So we split it up by slashes, and all these things get pulled out. And again, it inferred that this is times. And here's a visualization of times. And it's binded into days. Why is it binded into days? Because it's smart enough to understand, first of all, it's in the domain time. And second of all, the range is small enough that a good binning would be days. If this was a wider range, it might be months or years or so on. So the visualizations are being chosen appropriately to the data types and the data distributions, right? And this is a very lightweight, almost invisible sort of intelligence in the data visualization selection. All right. Similarly, we might want to pull out the call types here. So we can highlight this. And you can see it'll say, oh, I see you're trying to pull out capitalized uppercase things at the front of the column. And actually, if you look at the second row, that's not quite right? Because there's a 1 at the end of this. So we can give it another example. And it'll generalize and say, oh, I see you're trying to pull out things before a delimiter. And that looks better to me. We can double check by looking to the right here. That looks good. All right, and we can add this to our script as well. OK, so this looks better. We've now got pulled out these columns. Column 8, which is this disconnect reason column, is missing a whole lot of stuff. Something's fishy. So we're going to need to clean this up. But before we do that, if we click on this first row of headers, we'll get the recommendation to turn them into metadata instead of data. And so that's good. So we're pulling things out of the raw data and turning it into metadata. And now these columns, all the red went away, because these are all clock values now, and these are all integers and so on. Cool. If we go over here, we can look at the names of our columns in one place, and we can kind of drop these original source columns and just stick with the columns we extracted or the features we extracted from the data. So let's drop all these source columns and focus in now on this piece of the call detail records. Disconnect reasons seem to be missing a lot. Why is that? Well, I don't know. Let's click on the fact that it's missing and get a recommendation. It says, oh, maybe you're trying to keep the rows where the disconnect reason is empty. But notice something else that happened is it's showing us in each one of these vertical bars what percentage of each vertical bar is contributed by rows where disconnect reason is empty. Right? And if you look at this thing, you'll say, hey, wait a second. This whole bar is dark, and none of these are. And this whole bar is dark, and none of these are. There's a correlation between the disconnect reason being empty and these other 2 columns. And if we want, we can just look at the rows that match. And you'll see exactly what the bars are telling you. When the disconnect reason is empty, the duration tends to be really low, probably all 0. And when the disconnect reason is empty, there also tends to be SMS messages. these aren't calls at all. These are text messages. And they're kind of polluting the data we want to look at, which is how many people have calls that end abruptly, and what's the distribution of lengths of calls. And so you hover over this bar, it says SMS, and you look down here, sure enough. You hover over this bar, it says, yeah, it's 0 to 90, and you look at it, it's mostly 0. What we want to do is take the second recommendation. Let's get rid of all the SMS messages. Let's focus on the real messages. And now look at the duration distribution of the remaining data. There's a much more reasonable distribution of call lengths than we had before. Before, it was all skewed to 0, right? Because we were masking the real distribution with all this noise. OK. So now, very quickly, we've winnowed this thing down from an unstructured mess to actually a data set where we've sort of filtered out the data we're interested in. So that's nice. And now, what we really want to do is boil down this per call data to per customer data. OK? And so that's easy enough to do. That's just an aggregation. So we can go into an aggregation interface, which is not unlike what you'd see in a number of other sort of data analysis tools. We're going to group it by customer ID. And of course, ours is much more interactive and lovely than most other tools. But per customer ID and per reason that the call was disconnected. And the reasons seem to be 11 or 19. And we can work on that in a minute and decode them. I want to count up how many calls were for each disconnect reason. Okay? And so now I've boiled down the data to per customer per disconnect reason. Disconnect reasons, I've a data dictionary. I can look up what these disconnect reasons mean. I happen to know this because I'm the telco guy. All right? And so I can look up this column in a data dictionary that converts codes to descriptions and quickly convert this into text. So now I know it's call ended or it's call dropped. 11 is call ended, 19 is call dropped. Very nice. And now I can look at this data. I say, for a particular customer, how many calls ended and how many calls dropped. Okay? And I might want to compute those as percentages rather than as counts. And to do that, I have to do a little Excel formula, right? So here's how you do an Excel formula in Trifacta. You say derive value. What I want is this row count field divided by the sum of the row count field. But I don't want that sum over the entire column. I want it per customer. So this is the number of, for each row, it's the row count divided by the total row count per customer. And you can see we're getting percentages over on the right. Percentage ended, percentage dropped per customer. If you like, you can multiply this by 100 and turn it into percentages. OK. So nice. Now we've got percentages of calls ended, calls dropped per customer. Let's focus on dropped. And so we'll keep only calls dropped. And at this point, what do we have? We have a column here per customer that tells us the percentage of calls that were dropped. And this is a feature, a statistic, that per customer that tells them how much bad experience they're having with the service. All right, and at this point, we can now have a per customer statistic that we can correlate back to the customer data. And so we'll join it back with the customer data that we looked at before. Here's our subscribers table. We'll join it through. Trifacta will help make the joining easy by saying, hey, I think you should join it on these two columns that are named the same and have the same data types. So that's good. And in the output of the join, I'd like to pick the percentage drop thing we just calculated. And then per customer, how long have they been a customer? What's their customer status? Maybe what state do they live in? So I can plot them on a map and things like this. And we do that, and we're all set. Okay? So now we've got a data set that we could actually do an analysis on. We could look, for instance, for a correlation coefficient between percentage of call drops and how long they stay with the service. Right? And so the thing that we've done is this whole business was done on a sample. Remember my little eyedropper. Because I have this in a high-level language up here, I actually have compilers that will compile that high-level language down to one of your favorite runtimes. And so you can compile this and turn this into a script that you can run in Hadoop, in MapReduce, or in Spark on the full data set. Okay? You can just fire that job off right now, or you can put it in a scheduler. You can run it every night on the new logs. All right? So this is a way to go from prototype to deployment, right, with the touch of a button. And we won't do that right now. But what I will show you instead, very briefly, if I can find it in I didn't get a chance to pull this up, but I'll show you what a typical outcome of this process would be. At this point, you have a nice rectangular racked and stacked data set that you can load into a tool like Tableau for data visualization. Okay, and I'll show you what that might look like right here, because I already did that data visualization in advance. So I will not give you a Tableau demo other than to show you the output. But here's the kind of thing you might cook up as a dashboard in Tableau based on that table. If we give our friends from Tableau a chance to load up. Come on. Well, maybe not. One more time. Cool. Tableau, also a lovely piece of software that came out of data visualization research at Stanford, by the way. Sometimes it crashes, but we all do sometimes. So here's a visualization right? We took our state information and our percentage dropped, or actually 1 minus our percentage dropped. And you can see things are green, but in New Mexico and Minnesota and Maine, there's a lot of calls dropped. And maybe those are places we want to put more cell towers to prevent customers there from leaving the service. And remember our original hypothesis. There's a correlation between the successful call percentage, or rather the number of calls dropped, and people dropping out of the service. And sure enough, if you look at it, when you have a low successful call percentage, you're more likely to see orange, canceled customers, who have short periods of time with the service. And so yes, indeed, if customers are getting call drops, you should send them a coupon because they're not happy. Right? And that's the kind of churn analysis type of thing we're trying to go for. That's a task you can imagine the business data analyst, the guy deciding about who sends out coupons, doing that work, right? But in the traditional data environment where you had to get someone at the data warehouse to model that call detail log, load it into a relational database, provide an extract, that would have taken months of sort of trouble tickets and requests with IT, right? And why did this become so easy? It wasn't fundamentally because it was visual. All right? It wasn't that this tool was menu-driven. That's not what made it easy. What made it easy was that new interaction model, where the machine did some of the work, especially of the specification of the coding. And the analyst focused on features in the data that interested them, and then outcomes of those recommendations from the software. All right. So I think that's most of what I wanted to do today. Quickly go back to the software. How does this thing work? Sorry, the PowerPoint. Well, the reason the company is called Trifacta is because there's this sort of 3 things you put together: people, data, and computation. And I would say fundamentally we didn't make a breakthrough on any one of these things. It's the way that they come together where the breakthrough is. So clearly the people piece is this human-computer interaction. We need an interaction design that helps people tell us what features in the data interest them. Features are things you feed to machine learning algorithms, right? So when I highlight little substrings, or I click on bars in bar charts, those are all features that we feed in eventually into machine learning algorithms to predict statements in the language. And then we want feedback right away in that user interface on what does the data outcome look like, and what is that data-specific language that I'm trying to utter, trying to do to the data. Getting the right language is key to the puzzle. Okay? Think about this. That language wrangle, what purpose did it serve? Well, it was a high-level language so the user could see step-by-step how they were changing the data. We didn't type 4x in thing, we didn't say go to line 7. It's not that kind of a language. It's a high-level language, right? That said things like, this row of data should turn into metadata. It's a very specifically designed language for this task. So it matches the mental model of the user. And importantly, so it's interactive. It matches the mental model of the user. Importantly, it's predictable by algorithm. So we had a high enough level language that a machine learning algorithm could actually predict what you're trying to do. It's very hard to predict your next line of Python code because you could say anything in Python, right? And then finally, the machine learning piece of it, right? We're training a machine learning algorithm to take input as visual features in a UI and to predict output as sentences in a language. This is a rather constrained and interesting machine learning problem. Okay, so these things come together in this very interesting way to really change the interaction model at the end of the day and the productivity for a user. It's a very user-centric design that pulls in a lot of pieces of computer science and kind of puts them together. So that's kind of the pitch. I'm happy to take questions. Yeah.
So I work in a pretty traditional ETL kind of shop where we're doing all that transformation and creating a production environment data warehouse that a bunch of users are doing. Sometimes nobody really understands the data, so we're creating this knowledge, but a lot of times we have subject matter expertise that know it that are outside of our group. So can you comment on how this kind of a tool might work in an environment like that where we want to have subject matter expertise that then can get transformed into that portable code that then gets into a production environment, so that everybody can benefit from that and other users can benefit from it?
Great. So, this is partly an organizational question, obviously. If you're in a traditional IT environment where sort of the subject matter experts or the business users, however you talk about them, are in one camp and sort of IT is in another, that communication problem is already hard, and that's part of the inefficiency of this. But what I've experienced talking to IT managers over the last 2 years and CIOs of big companies is that there is a deliberate shifting of the needle where IT is trying to enable the business units to do some self-service more and more. So BI is sort of the sharp end of the stick, getting Tableau on people's desktops and things like that. And this is dragged along, I think, second. And so I think there is right now today, you read about, if you follow these things, hybrid IT models or what is it, settlers and and I can't remember all the names, Cowboys and something, but trying to enable business units to do more of their own work. I think that is actually happening. That said, if you're in a very traditional model, this can be used as a prototyping tool. So what we see with some customers is that there's a data science team and they write stuff in Python, and then they get it all working on some environment, and then they translate what they did in Python to Microsoft Word or email, right, which describes what they did, and then they send that to the IT department, who translates from Microsoft Word or email back into Java, right? And that process is long and very lossy. It's like a game of telephone. So if you can have actually a deployable implementation, and this is one of our customers does exactly this now, is they're replacing that interaction with, I take the output of this thing, the high-level Wrangle script, as well as the pig jobs that it compiles down to. I give those to IT. They can actually just run the jobs, but they're IT, so maybe they're not going to trust that. But at least they have a reference implementation, right? So that's one way that I think this evolves. The more aggressive way that this evolves, and we've been focused on the Hadoop environment for this in particular, is to say there's an infrastructure software shift going on anyway, which is reflecting some of this. So the model of having a big data lake where things can be unstructured and loaded without schema, and then both the business units and IT gather around a single watering hole, that's another way that this can come into being. But you don't necessarily have to buy into that notion to get value out of these kinds of tools.
Couple questions. Do you have connectors for all kinds of databases? Do you connect to SQL databases and SQL implementations? The other one is, do you get this kind of performance with huge data volumes, or is there a limit to that?
Great. OK, so very tactical product questions. That's great. Just fine. So first question, do we have connectors to lots of different data sources? And the answer is no. So traditionally, the ETL vendors, who are sort of the very old generation version of this, would make money by making sure that you paid extra to connect to your mainframe database, you paid extra to connect to Oracle, you paid extra to connect to SAP, what have you. What's happened with open source is that a lot of that stuff is commoditizing. You know, the open source community is building a lot of things to load from SQL into Hadoop and so on. And so we very deliberately decided not to invest in this sort of 1990s sort of era, milk the customer on connectors. We're assuming the open source community is going to take the bottom out of that market. We don't even want to sell that software. Nobody wants to write that software. People who have to will. And we're focused on data that's already been landed in a file system environment. So that's decision number one that we made on that front. Your second question was about scale, and that's something I glossed over very quickly. But if you remember in the animation, the software actually pulls a sample of the data. And so the interaction you saw was over a sample. Those data distributions and histograms you saw were a sample of the data. And so we have a feedback loop actually in the tool. After you get it running on the sample and you click Run Job in Hadoop, then we scale up as Hadoop or Spark scales up, right, to run on the full parallel large data set. But you need to assess the output of that job, because there may be needles in that haystack that you didn't see in your original sample. We pull those needles back. We give you data quality assessments. If things look strange, you can take the examples of the strange, pull them back into the UI, and continue to evolve your script to deal with that. And so fundamentally, we believe the answer, and this is best practice of the people I watch in the field, the answer is not make your system run really fast on a petabyte, because that's not really going to work. The answer is make that feedback loop of pulling a sample, working with it, and then turning it into production code, make that more efficient. So that's been our philosophy.
Yeah.
What you
question.
Sorry.
There's a question over there.
What you showed us was very impressive. Thank you. I'm curious, if you have to do data joins, how do you account for taxonomy differences between what you have and what you might be getting from a different system?
Great question. Very typical problem is the traditional data integration problem, if you will. You have two different data sets. You need to join them together, but perhaps they have different representations of entities. So maybe one of them has codes for products and the other one has names for products. Or maybe they both have names for products, but the names are not the same. And there's a mapping problem and a translation problem that you have to solve in order to bring these data sets together. So we have tools, which I didn't get to show you today, for doing things like canonicalization of string values into clusters and trying to address those problems. And then we also have the ability to register data dictionaries with the system and map through them. And I won't say that these are particularly surprising solutions to the problem. At some level, these problems just kind of have to be beat over the head. But we do sort of address these problems in a fairly traditional way, and we try to recommend solutions to these problems through our machine learning algorithms as we go. There are a number of companies and a number of research projects that try to automate this. They'll say, oh, you know what, we'll crawl over all your data sets and we'll tell you how to put them together. And fundamentally, what that assumes is that data transformation is either automatable or not necessary. Right? That somehow I will magically know that your 472 is my IBM. Right? And that's unlikely to work, in my opinion. I read on Twitter recently where you learn all good things, right? The etymology of the word automate is auto, which means self, and mate, which means screw. Right? Automation is not the solution to this problem. And so providing those recommendations and interaction models has been our approach to it. But it's a messy, messy problem.
Yeah, hi. Quick question. So about this product, Trifacta, is it only done by someone need to interact with the tool, or is there an automated way to handle this? And one more question is that I was curious, like big data has become popular now, but we tend to forget that petabyte and those kind of data has been handled by space, NASA, when they collect data. So what kind of tools are they using, and how have the knowledge is able to transfer to our world here, I mean, civilian world?
Great. Okay, let's see. Wow, those are two completely different questions. The second one got me off on a rant in my head that I haven't even started saying, but I need to remember the first question.
Is it interactive only?
Oh, I see, yes. Once these scripts are written, you can actually turn it into a command line interface that you can run in a scheduler. And so typically if this is being done in production, after you get things looking just the way you want, you download this thing as a bundle, and then that bundle can be plugged into a Hadoop scheduler and be run on a regular basis in an unattended fashion. So typically we do that. We don't do totally automatic crawling of your data, because again, I'm not sure that that's really fundamentally useful. I believe people have to be in the loop on this stuff.
Yeah, one more question I have.
So I'm happy to answer your NASA question if you like.
Okay, sure.
Or I will answer your other question, but then you're done.
That's great. Please, do you handle non-structured data? I mean, here, how do you handle also if you're getting stream of data from IoT, like sensors, like
Okay,
one of the
I can't answer all these questions in the time allotted, so I will pick the NASA question because I think it's a really interesting one for us at the university. So absolutely, big data sets are handled in high-performance computing environments. They tend to have very particular data sets. Traditionally, the HPC community was looking at dense matrix data. Okay, so this is a particular workload that they have because of the physical processes they're looking at that lead to a class of algorithms and tools that have been very successful but are also very narrow. And when you go to places that are looking at text or the web or business data, very often they're not appropriate. So if you're trying to tear apart the web and understand features like what words are associated with other words in text, or if you're trying to do recommender systems for movies, these tend to be sparse models. And so you don't tend to use the same tools that the high-performance computing community has perfected. So that's just a technical sort of distinction. Sometimes you do, okay. The other thing my rant is that the whole model of the national labs and high-performance computing is that we as a society believe that we should be about 3 years ahead of Moore's law in the national labs so that we can have a competitive advantage over our enemies. And to that end, we will build special purpose computers and write special purpose software, right? So that the national labs are approximately 2 generations of Moore's law out front. And to me, this is a very questionable endeavor as a taxpayer. And so I have some issues with the way we've thought about supercomputing as a discipline, particularly on the hardware side, and it's mostly going away. Companies like Cray and so on are gone. Okay, so I think there's some evidence that this hasn't been a very efficient approach to innovation. But that's a fun conversation over beers.
One last question.
Yeah, so I mean, very, very cool stuff. I'm been very impressed with the idea of like writing code, kind of getting to like von Neumann territory. And I was wondering, what is your grand vision for this technology and what's next?
Great. Thank you for asking that question. Very nice. Professors love questions like that, so do entrepreneurs. So this particular class of technology, the way I like to talk about it is to change the way people work with data. And the reason that we focus on that is I think the people piece is super duper important. And I think the idea that people will have work, that data is a plastic medium, it's something that whose job will be to work with it all day, every day. To me, that's the problem we're trying to actually address here, is how do people work with data, and how do you make that work more creative, more efficient, more effective? And so for me, anything we can do to aid in that is solving like the biggest bottleneck in computing today, which is people. Moore's law has made computers so cheap and data so easy to gather and store. The hardest thing is making people as efficient as possible and being a force multiplier to human intelligence. So to me, that's kind of the grand vision, is how do you build interaction models with intelligence from the compute and intelligence from the people coming together. Very focused on the company, what I'd say is that we wanted to build a tool that solved a real problem in this mode. And with that, earn the trust of the community to be able to build more such tools that knit together multiple analysts and take recommendations across users and do all kinds of things that are somewhat more organizational than this individual user task. So that's somewhere where the company, I think, over time will move as well. Yeah.
Let's give Joe another big hand.